right. So have you had a chance to think about the problem that I mentioned, right? So you have, it's a little silly the way I worded it, but a teacher is working at some school. So you understand so just a few things to say about that exam question. To be or not to be means that, notice the way I made it is that you might have two sentences overlapping, right? Right, to be or not to be, right? So to be or not to be and another to be or not to be can borrow the some part of the last sentence. Okay, so think about it. We did solve similar questions together. All right, so well, you know, we can talk about what I mean afterwards, right? If you have questions after this lecture, we can look at the exam questions if that's what you need. So let's go with today's lecture. So again, have you had a chance, but just have anybody thought about this problem? Yes, you do find similar problems, I think. So a teacher working in a school has 101 students. Most of them are very nice, but only one of them is Dennis the Menace. And at some point, there is a prank. So she sits on a chair to rest, and she finds that she's sitting on a bed of pins, and she's very angry, and she goes to complain to the principal, and she wants Dennis expelled based on the following supposedly disputable evidence. So prank was perpetrated certainly by exactly one of the 101 students, and if Dennis were innocent, then the probability of this happening would be 1 out of 1,000. And the school has a policy of finding the student guilty and expelling the student as long as the likelihood of innocence is below 5 out of 1,000. I mean, just arbitrary numbers here, right? But what the question is, based on this evidence I and evidence double I, should the principal find Dennis guilty? What do you think? Sorry? So I guess you have not had time to think about this problem. So I guess we'll go through and solve. So here is one solution, right? So suppose it is known somehow, right? Maybe there is prior statistics. It's known that if you're given a juvenile delinquent out of 9,001, only one, on average, will commit this particular crime. Okay, or this crime is the frequency of this crime is 1 out of 9,001, given a population of criminals. Okay, and what else you may suppose, right? So suppose that again, as given, is that the probability of evidence given that the person is innocent. It's a hypothesis testing of sorts, yes. So given that he is innocent, the probability that evidence will appear is 10 to the power of -3. That's what supposedly has been calculated. And suppose that the evidence, of course, if he's not guilty, if he's guilty, that is not innocent, the probability of that is then 1. Then the probability of innocence given the evidence. If you look at the information above, right, I should mention that, let's say, each individual good student, maybe this is the likelihood. 10 to the power of -5 is the likelihood. I'm just throwing numbers here, right? Is the likelihood that the person is is that a good person will go and do this prank. So then with this information, the probability of innocence given the evidence is the probability of evidence given innocence times probability of innocence divided by probability of evidence given innocence, probability of innocence plus probability evidence given lack of innocence times the probability the person is guilty. So based on the numbers that I obtain, if you plug them all in, you obtain the probability given this evidence that Dennis is innocent to be 0.9. You understand? So it still is extremely likely that Dennis is innocent. So that's called Prosecutor Paradox. And there was an actual case that involved the Prosecutor Paradox. And this happened apparently in '98. And some person named Sally Clark, she was tried for the murder of her two sons. Shortly after they were born, those two sons died. So during the trial, expert witness for the prosecution testified that the probability of a newborn dying of sudden infant death syndrome, which is SIDS, is 1 out of 8,500. Okay, so this expert witness calculated the probability of deaths due to SIDS in one family to be 1 over 85,000 squared, or over. So basically, it's 1 out of 73 million, roughly. Okay, and therefore the conclusion that this expert witness was proposing is that given that Clark is innocent, the probability that this situation would happen, that you would find that two infants are just dying, is 1 out of 73 million, and that was evidence enough to convict her and sentence her to jail for murder. What do you think? I mean, I went rather fast through the previous example. What do you think? I mean, that's the question. I mean, Dennis the Man is rather contrite story. Who knows? Maybe it doesn't tickle you. Were you in the jury? Would you have convicted this person based on this testimony? So Shulamit says no. That's a very good point, Josh. Right. So independence is an assumption here, right? So one important thing to note is that 1 out of 85,000 was squared. That means that there was an assumption that sudden death syndrome, it's like a strange visitor to your house. It's equally likely to visit any 1 out of 8,500 families each time, right? So sudden death syndrome might be, I mean, it's just a poorly diagnosed thing, I suppose. It's just all sorts of strange and unexplained causes by which maybe an infant might die. So in this situation, if this information is true, if it's 1 out of 85,000, then you might think that if you're witnessing a family that has this problem, perhaps there is genetic defect, and perhaps knowing that one infant dies, at the extreme case, it's almost certain that the other infant will also die, right? So there might not be independent at all. So that's one issue with this problem, is that why do we square it? Okay, it's not independent at all. But let's suppose, Josh and the others that answered, let's suppose that sudden death syndrome is like the angel of death visiting a family at random, right? They just randomly picks a family out of 85,000 families, visits a family, and boom, and kills that child. And then if you have any other child, the probability this angel of death visited twice is then indeed 1 out of 85,000 squared. Let's suppose it is independent. If that were the case, would you have convicted the defendant? You understand what I'm asking, right? In other words, it's not due to a disease, it's due to basically, let's say it's the likelihood that a brick falls on a person's head, I don't know, right? And randomly, right? It's not under construction. Just a random event, completely random event. Every 1 out of 8,500 families that have a bunch of children, this can happen to them, to one of them. you know, and for simulating it happening twice, it's just, you know, you go through the same collection of people and you pick one family, and again this happens. Would you have convicted the person if this number is true? So the most important thing, and that's what David possibly is saying, right, is that this is the probability of evidence given innocence. Okay, so a priori, you see, you're assuming innocence when you calculate the probability 1 out of 73 million. It's already assumed that we are dealing with an innocent person. Okay, so you have to be very careful here, right? So it might kind of be, you might think this way, right? You might think, well, if innocence is indeed true, I am seeing a very unlikely evidence. I don't believe that the hypothesis of innocence is true. But you are only safe when you are calculating the probability of innocence given evidence. You understand? So if you're already assuming a person is innocent, then no matter how, by logic, no matter how unlikely is that evidence to happen, if you assume that innocence is true, then the person is just innocent. It's just an unlikely evidence that popped out. Okay, well, you're more safely, you should more safely calculate probability of innocence given evidence, because truly what happened here is that you have 2 children that died. Okay, that's truly the evidence. We have 2 children that died. We do not know if a murder occurred or if it did not occur. Correct? That's what Shulamit is saying. We do not know if there was a murder or not. But we would assume that if the probability of innocence is very low, then we will believe that the person is guilty. You can never, ever be absolutely certain with 100% certainty that the person is guilty of anything. But you use probabilistic reasoning to say that if it's very unlikely that the person is innocent, then the person is guilty. OJ, well, I don't know. I mean, OJ, it was a whole long story, right? It's a question. You see, I mean, you might wonder. I mean, you might kind of in this class you might switch and say you would not have convicted this person, but maybe you would have looked at this Clark and you would not like her. You just think, well, I'm certain she is guilty, and you would have convicted her, right? People don't necessarily just go by evidence. But let's say in terms of probability, is this a valid argument? And this is, as I mentioned already, it's called prosecutor error. And I try to demonstrate in that contrived example above is that you can, and you can do the same thing in this example. If it, so we are trying to figure out, this is what we know, right? We know the probability of evidence given innocence, but what we want is the probability of innocence given evidence. Yes, and the probability of innocence given evidence is given by the Bayesian formula to be this expression. Yes, so notice what can happen here, right? So the evidence given that Clark is guilty of murder would be almost 100%, maybe even 100%, right? So this number is, you can just assume it's equal to 1, right? So what can truly happen? And the thing is, the question is, what is the initial probability of innocence? That you have a mother, what's the probability a mother will kill 2 children? And this probability here is, the probability that mother will kill 2 children, this probability is very small. Probability of I complement is very small, and therefore the probability that the mother is innocent a priori is very high, I'm sorry, right? It's a very, very big number, close to 1. So what happens is that you might expect that this part, the probability of guilt is very low, so you might expect that this part might be a very small number, and then the probability of innocence might be this part of the numerator divided by this part of the denominator and almost be equal to 1. That's how we got 90% in the previous example. You can tweak the numbers, right? If the probability of innocence, if you can calculate it, is very high, then it could be that this fraction almost looks like numerator divided by the left part of the denominator, which almost looks like 1. Okay, make sense? So we mentioned that regarding why I introduced it here. We mentioned it about a coin. You remember we had a coin that we did not know its probability, but we flipped it 100 times. We had, well, sorry, 1,000 independent trials, and 550 of those trials ended up producing heads. And the question is, how likely is the coin how likely is this coin to be fair? And that's what we will hopefully discuss later today. All right, guys, you're eerily quiet. Right? Strange. So here are a few more questions back to the topic of still finishing the topic of application of normal distributions to the central limit theorem. Why the central limit theorem makes normal distributions such a good tool. Let's suppose we have this situation. We have ideal size of a first-year class in a particular college is, let's say, 150 students. So 150 students, should be admitted. 150 freshmen should be admitted to college every year. And on average, it's known that about 30% of those accepted those will actually go to the college, right? So if you get acceptance letter, the likelihood you will go to college is 0.3. Sorry, Romeo, what did you want to say? Okay, go. So guys, so you see, so the question is, if we approved 450 applications, what's the probability that more than 150 first-year students will actually join this college? Can you calculate or at least estimate? Set up. I mean, estimation can be done later. We still have a bunch of things to cover, so let's work through this problem. So here is what happens here, right? So x, it's a x is the sum of the random variables x1 through x450 for each individual student that accepts or rejects the application, right? And xk will equal to 1 if the application is accepted by the student and 0 if rejected. So those are all people that are eligible to attend this college. So first, I want to calculate the expected value of x. Well, the expected value of x is simply 450 multiplied by 0.3. That's over here, right? I need the expected value because, well, that will be the mean that I will use for the normal approximation. Good. And the other thing is, I need to also calculate the standard deviation. So I calculate the variance. Variance happens to be, since each of those students supposedly accepts or rejects independently of the other, they don't necessarily know each other. I mean, they should kind of not be affected by each other's decisions for this to be fully true. So what should happen is then that the variance is the sum of the variances, right? And that means the variance is 450 multiplied by probability of accepting and also multiplied by the probability of rejection. Okay, so 0.3, 0.7. That's because this is binomial, right? If you remember the binomial, or you just, we did this calculation several times. So we have this. So then the way I set it up, right, I said, okay, so I want to know what's the probability that 151 students or more will go to this college. So I said x is bigger than or equal to 151, which I then convert to the z-scores by subtracting the mean and dividing by the standard deviation and doing the corresponding thing to the score. And then I roughly get probability that z is bigger than or equal to 1.65, which is about 5%. Okay, so about 5% likelihood that this will happen. So there is one more question here that I wrote out, but I really want to move on and talk about the beta distribution. So I will skip this question. You are free to look at it later. All right, so today's topic is beta distribution, and it's hopefully a very interesting topic. So first of all, the beta distribution is a continuous distribution over the interval 0 to 1. And it is a generalization of uniform random variables over 0, 1, or the idea is with beta distribution, you can simulate many distributions that can arise over the interval 0, 1. Okay? And I will explain what's so special about it in a moment. But first of all, this is the definition. So a random variable x is said to have a beta distribution with parameters a and b if the density function is given by 1 over beta ab. I will explain in a moment what this number is. And x to the a minus 1, 1 minus x to the b minus 1, where x is between 0 and 1. And this beta is just the integral of x to the a minus 1, 1 minus x to the b minus 1, so that the area under f from 0 to 1, it has to be equal to 1. Yes, so that's why we have this thing. Okay. Notice, of course, several things about this distribution. For any, well, except of course where a is equal to 1 and b is equal to 1, x and 1 minus x, basically this function f, I'm sorry, at 0 it's 0 and at 1 it's 0. For all cases except where a and b are equal to 1. So we will write that x is a beta distribution by writing something like this. It's a beta distribution with parameters a and b. So here's what happens if I set a equal to 1 and b equal to 1. Then of course you can see that this will be 0. This will be 0. So this is just 1. So if a equals to 1 and b equals to 1, beta 1 1 is simply it's simply the uniform distribution over the interval 0 to 1. And there this is a guideline for how to roughly imagine the shape of the distribution. So if a is less than 1 and b is less than 1, then the distribution is U-shaped. So I think I accidentally said when a is only equal to 1 and b equal to 1, but here if a, I should correct myself. If a is less than 1 and b is less than 1, then you have a U-shaped distribution. On the other hand, if a and b are bigger than 1, then it would be frown smile. And if a is equal to b, the probability density function will be symmetric about 1/2. If a is bigger than b, the it would favor the density will favor larger values, and if a smaller than b, it will favor smaller values. Okay, so that's just a shape of the distribution, not so important for the purposes that we will talk, but just, you know, the idea is, in essence, you can mold the curve to be pretty much anything over the interval 0, 1. Okay, so here is first of all, we will need to figure out how to calculate beta at a, b, where a and b are positive integers. So here, guys, and be ready. Now it might be hard. We are going to use a combinatorial argument to prove that the integral from 0 to 1 of n choose k x to the k 1 minus x to the n minus k dx equals to 1 over n plus 1 for any integer k between 0 and n. So here is the combinatorial proof, guys. So imagine that what we are going to do is we have n plus 1 points or n plus 1 particles or atoms, and those particles will be randomly placed on the interval between 0 and 1. Okay, they're just going to be randomly thrown over the interval 0, 1, kind of like this. One of the particles is colored red and the others are colored black. So we have n black particles and 1 red particle. Okay, so then you might define the following random variable x. So x is the number of black particles before or to the left of the red particle. So x could equal to 0, means that red is the leftmost particle in the interval, or it could equal to 1 or 2 or all the way to n, right? So when x equals to k, that means that exactly k particles are below the red particle, or to the left of the red particle. Okay, so how do we calculate the probability that x equals to k? Are you with me, guys? It's very quiet here. So far, what I'm saying, so far, are you following what I'm saying, guys? Not too much trouble? Good. Thank you, Isabella. Where are you hiding, Isabella? I don't see you. And the rest of you. Okay, so here is what's happening. So I need to condition, right? So look what can happen here, right? If I know where the red particle is, let's say it happened, I just keep track of where the red particle went. So let's say the red particle ended up here, and then we have additional black particles, and each black particle is equally likely to be anywhere on the interval. Are you following me? If given that I know that red is at point P, as I drew over here, then the probability we have all those particles that are trials. Where is this particle going to go? It either goes here or it goes here. It will be a success if the particle goes here, and a failure if the particle goes here. Make sense? So because particle 1 is uniformly distributed, it's equally likely to go anywhere. It's randomly placed. Randomly means uniformly distributed. Given that red is here, the probability particle 1 is below or to the left of the red point. It's the area under this curve, which just happens to be P, right? So the probability that 1 will be a success, that particle 1 lands between 0 and P, the probability of that is P. And the probability of failure is 1 minus P. Do you see that? Good. So what happens? The probability that x equals to k, given that I know where the red particle is, that's just a binomial random variable. N choose k, the probability x equals to k, if I know where red is simply n choose k, p to the k, 1 minus p to the power of n minus k. Good? It's just a binomial, right? And this is just the outcome that exactly k of those particles are in here. Yes? Because each of them is an independent trial, and each of those independent trials has success probability P, failure probability 1 minus P. So that's if I know where red landed. Good? So since R is a uniform random variable, its density function is 1 over the interval 0 to 1. So we are going to apply, I'm hoping that my Riemann integral presentation is going to help you understand, right? We're going to pretty much apply Bayes' formula where we have many conditions. So here is how I think of it. I hope it's not going to be too confusing. I'm going to condition on the different places where the red particle was placed. But for a moment, it might feel convenient to imagine that the red particle is a discrete random variable. It can only be placed among m places. You see, that's why I say Rm. Rm means that I divide the interval into m parts, m segments, and the particle is either in this segment or second segment or third segment or fourth segment, etc. So that's how I represent its actual position, right? So the probability the particle lands at j divided by m, where j goes from 1 to m, is going to be, that should be m, I'm sorry, right? That should be m. So it should be j, the probability that r sub m equals to j over m is the density function at j divided by m times 1 over m. Before I move on, do you understand why that will be the probability? Remember how, yes. So do you understand what's our problem? If I know where the red particle is located, if I know it's at point P, then given that information, it's not hard to figure out the probability that exactly k out of the remaining n black particles are to the left of this point. Is that clear? Good. So that would be a binomial distribution. The problem here is that I do not know where this red point will appear. It could be where I'm pointing now. It could be here. It could be here. So there are many conditions. In fact, you might think there are infinitely many places where the red particle might appear. So I want to, what is k? K is just how many of those particles I want below. So let's say k equals 0. That means I want this. What's the probability that the red particle is leftmost? If k equals to n, that means what's the probability the red particle is rightmost, right? When I throw those particles onto the interval, then I can observe how many of the particles are to the left of P. Make sense? So that's what x equal to k is, right? It means what's the probability that I observe exactly k particles? They're altogether n particles. What's the probability I observe exactly k particles to the left of the point P? Oh, to the left of, sorry, the red point. So what I do next is you see, because P could be in so many places, perhaps it might be helpful to think of the red particle as actually a discrete random variable. So it only can appear in finitely many places. And how I do that is that I imagine that that the particle, you can see like the actual red particle, you cannot truly tell, you see this thing that I'm moving, where exactly is it? So this looks like it landed at a point, let's say at 0, or if you want to the left of 0. I can imagine the rightmost edge of this shining light to be the place where the particle landed. So it either lands here, or it lands here, or it lands here, or it lands here. Right? So in essence, so what you can imagine is that if you divide the intervals into a finite but very thin, basically to finitely many but very thin line segments, the line segments would look to you like one point. You cannot distinguish them from one point. And that's, so then that's, in that sense, I want to try to simulate the discrete situation. In other words, imagine that this red light can actually only appear in discrete number of places. Okay, And what I do then is I define a random variable Rm, which means it can only appear in m places. And then the position of this appearance will be j divided by m, where j is from 1 to m. Okay, so j divided by, so if j is equal to 1, that's roughly here. If j equal to 2, that's roughly here. And when j equals to m, that's at 1. It means the particle appears at 1. So it makes sense what this variable is. And then I ask, what's the probability, this should be m, that Rm equals to j divided by m. Now, we know that the actual R is a uniform random variable. But again, how did we even construct it, right? So I always imagine that the uniform random variable is just a variable. It's almost like a discrete random variable where the probability of something happening is, let's say, so that the probability that this outcome here happened, or let's say this point P happened, is the area of a thin rectangular column, where the height of this column is given by the density function, and the width of the column is dp, is just the difference of the x-axis. In this case, if I am asking for the probability that that this number is selected, it's roughly the density at this number times the dp, or the width of the thin column. You understand what this is saying? So this is saying, let's say if this number is p, this is saying this is the height times a very thin width, and that will give me the probability. That's how the density function was defined if you looked at it. Do I make sense? So what is integration? Integration is nothing more than sum, you understand? So if you realize that and realize it well, then it's not too difficult to work with. So why is it that we have areas under curves? Area under the curve really just means, I imagine, very thin rectangular columns. And I add up their areas because their areas are supposed to represent probability. And how that was generated, I have very thin histograms. So I by default, I make it so that area would work here. Do you follow? Yes. So the others got quiet, right? So I'm hoping you're following. So this is then the probability. So then what is the probability that x equals to k? That is the summation. I'm just using Bayes formula. Summation j starts at 1 to m. Probability x equals to k. Then this should be r sub m. But again, right, r equal to j over m. Probability r is j over m, which is we know this, right? This means that the probability of success is j over m, and the probability of failure is 1 minus j over m. And so the first part here is simply a binomial part times this, which is the density function, times the width. Now, if you look at it, you recognize the Riemann integral. This is just a Riemann integral. So when you take the limit as m goes to infinity, if m is very large, as m goes to infinity, that sum is just a summation from 0 to 1, n choose k, p to the k, 1 minus p to the n minus k, times the density function at p, dp. Which, because the density function in this case equals to 1 everywhere, I can simply ignore it and I get this integral. Do you follow? I got this integral. So this integral represents the probability that exactly k particles will be to the left of the red particle. It's the integral of this, which looks like a binomial distribution. So guys, before I move on, do you understand what I just said? Do you understand what happened here? I just applied, so when I convert to an integral, it's nothing more than realizing that this is just a fancy sum where we take the limit, right? Where the matches or the rectangular columns, as I imagined them, they become very thin. Did you fall asleep? Guys, I need proof of existence. Yours, I mean, right? Mine, forget about it. Proof of existence. Good. How to prove existence? Here, right? Statistically speaking, right? So again, I want to be sure I'm explaining possibly difficult things, or possibly not, I'm not sure. I'm explaining, I have some pictures in this document, right? Here is area, right? So this is supposed to be a density curve, and there is area. Now, what should you imagine when you calculate probability? Or why is the area under the curve probability? What I imagine is that this curve is produced by many thin rectangular columns. So they are going up, rectangular columns. So they're very thin. dp is or dx, whatever we're calling it, right, is just the width of the column. And what is this? This is the height of the column. So let's say, why is it this high at 0.52? The probability of getting an outcome roughly 0.52 here will be the height of this column multiplied by roughly its width, right? Which you truly model by an integral. This is just summing over all those infinitesimally thin rectangular areas. Make sense? So what I did over here is exactly that. It's very simple argument. I got to this integral. Why? Because I used Bayes formula. Bayes formula, you remember it, right? In the discrete case, I just apply it like this, right? It's the probability that x equals to k given all the possibilities that r can equal. So I made r a discrete random variable, and I get this sum, which you recognize is just in the limit as m goes to infinity. That's the integral. So please let me know if you understand what happened. Say yes, possibly, or respond, please, guys. Possibly, mostly. 2 people responded. The others are completely confused. Mostly. If you could tell me, maybe I can dispel some confusion. Right. So what can I dispel? Right. So again, right, you understand that if I dealt with a discrete random variable, I just condition on all possibilities of r. It's very easy to calculate probability that x equals to k, given that I know what r is, as I showed in the picture above, right? If I knew what r is, then I can calculate it. So if r could only be in discrete many places, let's say 7 places or even 100 places, right? What I do is I calculate the probability that x equals to k, given the probability that r is in one of those places. Right, times, so basically probability x equal to k given r is in first place, where that's when j is 1, then when r is equal to second place, third place, etc. And I multiply by the probability that r equals to that place. Which, if you write it out in the sum, so that's why I made it a discrete random variable. It might be for some of you easier to right away go to the integral. That's fine. Some of you have studied physics. You might be more comfortable with it, right? So I just try to show you how it becomes an integral. So it's just a summation, a discrete sum. And that discrete sum is better and better approximation of the actual situation when the number of steps is very large and where each step is very thin, very small, right? J over m. So it means that the segment is very short. J over m, 1 over m will be a very small segment eventually. Right, 1 over a million, it's a very, it's a micron, right? If I represented this curve, if I represented r by million possibilities, in each thickness is 1 out of million here, it will be indistinguishable for you from an actual continuous curve. So we have this summation, and if m is large, this sum is essentially the probability that x equals to k. But this sum is just in the limit the integral from 0, 1 of n choose k p to the k1 minus p to the n minus k times the density function f, which happens to be 1 because little f is the density function of the red particle, and it's the same density distribution for all the others, right? But it's identically equal to 1 because it's uniform. So we get this integral. Okay. Now, on the other hand, so we see I get that this integral would be one way to calculate this probability. And it's pretty complicated. I mean, you have to use some sort of U substitution, blah, 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 right? So this integral is fairly complicated. Let's see how we can use combinatorial argument to figure out that there is another way to solve it. Now, every single variable, every single particle, the black particles and the red particles, are equally likely to appear in every order. Do you understand? Right? So if they are truly randomly placed on the number line, there is no preference to any order. And they're altogether n plus 1 factorial possible orderings of those particles. Do you agree? Right? N plus 1 orderings of those particles. Now, how many of those orderings will correspond to exactly, exactly k particles, black particles below or to the left of the red particle? Can you tell me that? Let's see if you can calculate, right? Do you see that all n plus 1 factorial orderings should be equally likely? Because again, that's if it's random, there is no preference to any particular order. So I'm equally likely to see 1, 2, all the way to n plus 1 as I am any other permutation of those numbers, if I read from left to right. Now, if that's the case, what's the probability that there are exactly k black particles below or to the left of the red particle? Come on, guys, this you have to figure out. That's back to second chapter. I'm already figuring out a very nice question, very relevant question of this beta distribution for your third exam. So make sure you understand it. Jeremy, how are you? Not showing your face? What's going on, Jeremy? Not feeling good? I appreciate that you came here. I was thinking you might be excited. You like physics, so I'm sure you deal with quite a lot of integrals and they come up like this. Come on, guys. Some proof of life. This you can solve, correct? Not such a difficult question, I hope. You see, I'm asking you this, right? So we have n plus 1 particles. And do you agree with me that every rearrangement of those particles is equally likely. If they are randomly placed on the number line, equally likely to see any ordering when I read it left to right. If that's the case, that what's the probability that, let's say, just begin slowly. What's the probability I see the numbers 1, so I see first particle, then to its right, second particle, third, fourth. What's the probability I see this particular ordering? Let's start there. What's the probability I see this particular ordering? One? Oh, that means that I have to see this ordering. That means this particle will be always to the left of every other. Yes. And Erlina, you don't mean 1 over, yes, not with the, yes, yes. Yes, yes, Ugo. And yes, Shulamit. And Erlina, I'm assuming you mean 1 over n plus 1 factorial, right? At least for my last question. Great, right? So 1 over n plus 1 factorial is the probability that I see this particular ordering. Now, my question is, what's the probability? Now, it's not about a specific ordering, right? What's the probability that I will see exactly k of the particles to the left of the red particle, so which I labeled as n plus 1? What's that probability? That I see exactly k of them. Combinatorics guy, or chapter 2. Ugo, well, you see, Ugo, here is your formula is almost right, but you have to think of the full sequence, right? Full sequence here, right? So here you don't tell me if you say n minus k factorial over n plus 1 factorial, you don't tell me what happens to the other particles. I need to, when I think of it, I need to, what I'm doing is I imagine seeing all the possible sequences. There are n plus 1 factorial sequences. In how many of those sequences do I see k, exactly k, black particles to the left of n plus 1, right? So that's very simple. What do? You just eliminate it from consideration. Those are n factorial. Do you agree? I just n factorial arrangements here, and then just place this particle after the k. You understand? So I can permute all the remaining ones, and whichever is arrangement, one of them is in the k place, and then I just place this particle. So it's n factorial. Do you see that? You see how I did it? It's just I am considering. Remember, one important idea in probability, and that helps avoid many mistakes. You have to consider the full sample space. You have to really imagine the sample space very well. So when I assume that all the particles are equally likely to appear in any order, I'm seeing really just a permutation of those numbers. Okay, so there are n plus 1 factorial permutations, and I can imagine those numbers are written on cards. So if I want the red particle to appear exactly on the k plus 1 place, then I just once I permute the other n particles, I place it exactly after the k particles. So that will be n factorial over n plus 1 factorial, and that's therefore 1 over n plus 1. So this number, this integral, look how cool. This integral is simply equal to 1 divided by n plus 1. Right? Without any calculation or any calculus, I know this equals to 1 over n plus 1. It is very, very cool, right? Amazing, actually. And again, in light of my recent obsessions, again, right? This is something we will need. So here, Therefore, my goal was initially to calculate this beta of AB. So if A and B are positive integers, right? If they are positive integers, then what should be the corresponding? Then I can do the following, right? Then I can the beta distribution is just x to the a minus 1 minus x to the b minus 1, right? I need to calculate this integral for the number b. So for the number b, so what do I do here? I need to make it like a binomial integral, right? Like this integral. So what I do is I just have x, a minus 1, y 1 minus x to the b minus 1, and this number plus this number is a plus b minus 2, and this is my k, the number of successes. So I put a minus 1 over here. Okay, so I have this integral must, according to this formula we obtained, must equal 1 over a plus b minus 1. Y minus 2 will go only because look at it, right? So here it's written as k n minus k, but really what matters is that this number over p plus this number over 1 minus p equal to the total number. So if I begin, my goal again is now calculate the constant beta of AB, or this integral, right? X a minus 1, y minus x, b minus 1. Why do they put minus 1? That's to adjust for, let's say, there's connection to a gamma distribution, right? It's something that actually I made once a mistake and I don't remember. I just put x to the a and 1 minus x to the b, right? So the reason you put it as a minus 1 is to confirm with some other distributions. So that maybe we'll talk about it later. But what we're interested, why we started considering this combinatorial argument, is that we want to calculate this number in the special case where a and b are positive integers. Okay, so they're positive integers. So it's a minus 1, b minus 1. So this number plus that number, if I want to convert it to look like this, this number plus that number is a plus b minus 2. I just have minus 1 is minus 2, right? So it's a plus b minus 2. Now a minus 1 is the number of successes that I want to have, so that's why I put a minus 1 over here. And so this integral by the combinatorial argument that we had over here simply equals to this number plus 1, or a plus b minus 1 in the denominator here. Okay, and that now means now what this is just a number. I can factor it out of the integral sign and move it over here. So that tells me that this integral equals to a minus 1 factorial, b minus 1 factorial divided by a plus b minus 1 factorial. So here you have a nice calculation of a calculus type of integral. Okay, so let's now begin at least to talk about why the beta distribution is such a useful tool. So imagine that this is the problem, right? So I mean, that's how you would come up with a beta distribution. Otherwise, you know, you would never remember the stuff. Okay, so imagine this is the situation that you're trying to obtain. Very often, you do not know the actual probability or actual prevalence of an event, right? In the previous questions, it was given to you, but how do we know that? So suppose we have a coin that lands heads with a known probability p. Make sense? So that's just a simple example, success or failure. That might not be a coin, maybe it's medication. How useful is this medication? There is an unknown probability that it will cure a random person, okay? It's still a simplifying assumption, but there is an unknown there. Or how many people are sick, truly, right? How do you estimate that? So let's begin modeling it with a coin. So we have a coin that lands heads with unknown probability p. Our goal is to infer the value of p after observing n independent tosses of the coin. The larger n is, of course, the more accurately we can estimate p. We would expect it, right? So we perform a bunch of trials, we perform experiments, and we are not going to throw the coin infinitely many times. That's impossible, right? So it's only if you throw it infinitely many times and do the experiment repeatedly that we can truly figure out the actual probability p. But that's impossible, so we are going to throw the coin n times. So how, that's the question where the binomial, sorry, the beta distribution becomes useful. How do we infer p? So we can do the following, right? So first, if it's a coin that's completely unknown to us, we can assume without any bias, we can assume P is equally likely to be any number between 0 and 1. Do you agree? I mean, you might have a prior expectation of coins, but imagine you witness a new event, right? And you have no reason to believe anything about this P. So your setup by default is that P is uniformly distributed over the interval 0, 1, because it's the probability. Maybe the coin never lands heads, maybe it always lands heads, right? It's not a true expectation. Maybe if you see a quarter, you already had prior experience, so you already updated it. But imagine you are newborn and you're seeing this quarter for the first time. You don't know what a quarter is. You don't know anything about this coin. You know nothing about a particular event and its likelihood of success. So by default, you might assume the unbiased idea that it's the probability is uniformly distributed between 0 and 1. Do you agree? I would like you to. Okay, so you follow my reasoning here. If you're not biased, then you assume that P is uniformly distributed. Some of you might be biased. So more generally, if you agree that it's fine to assume the distribution is uniform without any experience, without prior experimentation, then you would agree that since the distribution we discuss here, beta distribution, is more general than uniform distribution, it's even safer to assume that the distribution is beta. So it's fairly safe to assume it's uniform at the beginning, and it's even safer to assume it's some beta for some values A and B, whatever they are, right? I will solve concrete examples. In practice, you would assume without any prior experience that P is uniformly distributed, and then you update it. Okay, based on what happens, you now can say something else. So in general, let's suppose that W, and I chose W because we're calculating probability of probability, so I don't want to use the letter P. W stands for Wahrscheinlichkeit, which is how you say probability in German. So this is then the initial distribution of W. It's the beta distribution. So beta it's 1 over beta AB of P to the A minus 1 minus P minus 1. This is what we integrate. This is just a constant of integration. This is the more important part here, right? That's the initial assumption on how likely the coin is to land on heads. And let's suppose that X is the number of successes or heads that we obtain. Okay, so we want to understand how the density function should be upgraded. So in other words, we want to find a new density function GP, which will tell you the density given that X landed K times. So in other words, the coin landed K times on heads. Do you understand what this is supposed to mean? It's like before I have no idea. Let's say I think it's equally likely. Now imagine I threw the coin 100 times and all 100 times came up heads. So now you might be suspecting that it's a two-sided, there are heads on both sides of the coin. You expect it's extremely biased coin, agreed? Imagine I throw the coin 100 times. First, I mean, you had no assumption, but now I started throwing the coin 100 times and all of them landed heads. So you'd say that must be an unfair coin. So that's what this is supposed to be doing, right? Where do you think the coin is biased towards, given that exactly K outcomes were heads? That's what we're trying to figure out. So I need to figure out the density function for W given X equal to K. That's called marginal density. We might talk a little bit about marginal density later on, but I think you will be able to follow this argument without the general description of marginal density. So perhaps the simplest way to obtain this function G is to understand what property it must have. And that property is this. If W is between P and P plus DP, and X is given X equals to K, that is supposed to be G of P times DP. Do you understand what I'm saying here? That means what? Suppose that we already have, this is the data, it happened. We had K out of N, K heads. Then I want to figure out what's the likelihood W equals to the probability P. So that's the same as because W equal to P or something slightly different. This is the width of my thin region, right? So P to P plus dP. If dP is very, very small, then essentially W is like P. Yes. If W is equal to P, then G is supposed to be the height. So G of P times dP, which is the width. Height times width is supposed to give me the probability. In other words, G is the height of G of P is the height at P of the corresponding thin column. You with me, guys? I hope so. It's possibly not easy to explain. So again, that's what I'm saying over here, right? That's by its very nature, that's what the density function is supposed to do. It's just like you imagine. I imagine I want to say matches. I imagine matches of different length, and they are stocked, and their tips are tracing the curve G. And if they are very, very thin, then dP is that thin width, and GP is the height. So essentially, it's just the sum of rectangles. I just imagine a very, very fine histogram. That's really what I imagine when I integrate, right? So just nothing more than just a histogram. So the probability then that GP, so GP dP is this probability, which it's much easier to calculate by changing, by conditioning here. So that would be probability x equal to k, W between P and P plus dP, given that's when W is here, right? And times P, that's the probability that W is between P and P plus dP, divided by the probability x equals to k. Right? So let's start to approximate what this thing is. So if we condition on W, right? So what is this? This is essentially saying that W equals to P. There's very little difference between P and dP. dP is infinitesimally small. So you see where my cursor is pointing. The first piece here is essentially the probability that x equals to k, given that W is P. And that is this. That is n choose k, P to the k, 1 minus P to the power of n minus k. Do you understand? Because now that becomes a binomial distribution here, and I know P. So it's this number. And next, I need to estimate, let's estimate this part here. A probability that W is between P and P plus dP. Original prior probability where that happens is I did sorry, I looked at it right. So it should be here, right? It's f of P times dP. Right, that's the prior probability. We assumed, that's our initial assumption, right? That we assumed that the density function for W is this little f. So probability that W is between P and P plus dP is essentially f of P dP. It's basically, again, that's the density function for W. The assumed prior density function, which before you conduct the experiment, we might assume this is 1. So this is now what happens now. Now we are going to solve this, right? Numerator here, this part of the numerator that we condition based on what W can equal to. And what we get is this value, n choose k, summation over all possible probabilities of P to the k, 1 minus P, n minus k, f of P. So this value here is what we see, what could W be, right? So this is conditioned on so basically from this information I'm trying to calculate probability that x equals to k. So that would be the integral from 0 to 1, n choose k, x to the k, 1 minus x, n minus k, f of x dx. You can, if you want to use P again. But you see this probability, x equals to k, just like before, I condition on what W might be, like I did very slowly for that R in the previous example. I just get that probability x equals to k is this integral. Okay, so I have all the pieces in essence, right? I have all the pieces. So what is GP/dP? That is this part, n choose k, p to the k1 minus p to the n minus k. This part here is from here, right? That's probability x equal to k, where essentially W is p. Now, then I have this part here on the numerator. That part, or the numerator, is fp dp, right? And then probability x equals to k, it's this part on the denominator. And then you look at it, all of it looks very complicated, but look at it, I can cancel all the dp because my goal is to get to gp. I cancel the dp, and I look at the numbers here, and I see this is a constant, and this is a constant. So really, that looks like GP looks like a constant times p to the k, 1 minus p and minus k, f of p. And when I expand f of p, I might have the other constant, but essentially I have the original distribution, or the original density. It's p to the a minus 1, y minus p to the b minus 1. You see this? And there is going to be a constant of integration, 1 over beta of AB. So I can move everything together and make it a constant c hat. In essence, I'm just looking at what's the essence of this distribution. There is a constant, and with p is what varies here. So I have this is the essential part of the distribution. That gives you the shape of the distribution here, right? And c is this number. You see, I just put constant together. So if you and then look at it. When I simplify it, what do I get? I get that if I group together all the p's and 1 minus p's, I get p to the a plus k minus 1, y minus p, b plus n minus k minus 1. Right. So, and this is another beta distribution. So starting with a beta distribution, I create another beta distribution, and that beta distribution is beta of a plus k, comma b plus n minus k. That's the distribution of W. And just again, you realize that what is the c? This complicated expression for c is nothing more than 1 over beta a plus k, b plus n minus k. It's just a constant that makes the integration of this part equal to 1, right? If I integrate this from 0 to 1, I don't get 1 necessarily. So I need to multiply this by a constant, by this thing, to get it equal to 1, which is this number. So in other words, I get another beta distribution. Did you follow more or less what I said? Our time together is over. I might repeat this explanation. We might start with an example over here, right? So if you could, of course, go over, I posted it already on my website, so you can find this. All right, so I guess I'll stop recording.